And look at this. There's a perfect spot on the worksheet to place my face, right there in that empty spot. There we go. All right, so this is Notes 2. Today is August 11th. So if you're watching this later and you're trying to kind of sync up which day you missed or what day you're trying to review, I try to put the Unit 1, Day 2, and the date in the title of the video. That way, if you miss a day or you're trying to go back and, like, well, which day do I need to watch? I try to make it easy to find the one that you're looking for. All right, parent functions with the greatest integer function, meaning we're going to basically add that to our list of parent functions. So there's hopefully a good list that you already know, but we're going to add one to it today. It is expected that you're familiar with the equations and graphs of many parent functions. Write the basic equation, sketch the graph for each of the following. So quadratic, that's fancy talk for what's a quadratic? A parabola. So y equals x squared. And we're just getting the basic shape down. We're not putting like little hash marks and hitting the 1, 1 and the 2, 4. Like we're talking big picture here to make sure we understand the shape. We're not going deep dive into details. Square root, well, that's nice when the name tells you what the equation is. So square root of x. Somebody want to trace that out with their hand in the air, what the square root looks like? Okay, good.
It looks like a square root symbol.
Looks like a square root symbol? I guess, kind of, maybe.
With the y-axis. Yeah, I guess.
Okay, I guess so. This and this. Cubic. Show me what the cubic looks like. Function aerobics. Did you guys do those last year? All that stuff. Cubic would be, this way or this way, depending on which way you're looking. Absolute value. That's an easy one to do with your hands. The V. Right? Absolute V for value. A set of bars to indicate absolute value. Okay, we're cruising through these because we hope you know those. Constant, you remember what this is like an easy one, but sometimes people forget what constant means. It is a straight line, but that straight line has a slope to it. That's not a constant value of y. It's a horizontal straight line. Yeah. Y equals C, or Y equals K, where C is a constant. Reciprocal function? That's a fun one to try to draw in the air. Anyway, I think you got it right. It's really fun to try to draw both branches with both hands. Okay, yeah, you can do it this way, but I like doing it. I think this is right.
Oh.
Right?
Oh, no.
I might be backwards because I'm doing it how I would see it.
Yeah.
Right, like that. How about I just draw it? Like that? Y equals 1 over x. Identity function, that's kind of a funny name. Do you know what that means? Identity means it's identical. What you get out is identical to what you put in. So if you put in 1, you get out 1. If you put in 3, you get out 3. So y equals x. That's where the name comes from. And I think you know what y equals x looks like. Okay, so that's review. You probably had matching cards in Algebra 2 with those, with domain and range, and maybe not. Maybe that's just level that does that. I don't know. All right, now the next function is going to be new. It's called the greatest integer function, or the step function. Most of the time I call it the step function because that's what it looks like. But I think officially it's called the greatest integer function. And this equation looks like this. It didn't print, so congratulations. It does not look like what you think it looks like right there. It basically has 2 bars. So it sort of looks like absolute value, but it's not like the absolute value of the absolute value, because that would be repetitive and unnecessary. It's just 2 bars. So it somehow the printer doesn't like to print the greatest integer function. So the domain of the step function is all real numbers, so you can plug in anything you like. The range, the output, again, you got to add the double bars on either side. The range, the output, is integers, also known as Z. That's kind of fancy talk. The fancy R is real numbers. The fancy Z is integers. So you plug in any number you like, and it spits out an integer. And here's how it picks what integer to spit out. It's the greatest integer, hence the name, greatest integer function, that is less than or equal to x. It's helpful to think of a number line. So I want the greatest integer, but it has to be less than or equal to the input. So if I plug in 3, I need the biggest number that's less than or equal to 3. 3. If I plug in 3.2, I need, maybe I should show what it looks like. I need the greatest integer of 3.2. So I need the biggest number that's less than or equal to 3.2. The biggest integer, I should say. So also 3. If I plug in 2.9, I need the biggest integer that's less than or equal to 2.9. 2.
Will it always be equal to? Or?
What do you mean?
Oh wait, no, right.
I plug in 0.1. I need the biggest integer that's less than or equal to 0.1. That's 0. Yeah, if you take the time to say it out loud, it's not hard to do. It's just a lot to say out loud. Now, be careful with the negatives. Negative 0.2, so I need the biggest integer that's less than or equal to negative 0.2. Uh-oh. So negative 0.2 is like right there. So I need the biggest integer, but it has to be left of 0.2. So it's negative 1. So the negatives is what throws people off. You got to really be careful about the negatives, and a quick sketch of the negative or the number line sometimes helpful. No one calls it this, but I think of it as the go left function in terms of the number line. Like, put yourself on the number line and go left to the nearest integer. So if you're at negative 121.3 and you go left, you end up at negative 122. Yeah. If you need to draw the number line all the way out there, don't. So, greatest integer function. Here's what it looks like. Again, the printer doesn't like it, so it won't print the formula for it, or the picture. And now you know why it's called step function. Because it looks like steps. And you can see it's a function because it passes the vertical line test. Step functions make for interesting, and you know what interesting means when a math teacher says interesting. It's kind of a synonym for hard, but we don't want to say hard. Makes for interesting questions when we start calculus. Greatest integer function feels weird and strange, I'll grant you that. But so did all the others the first time you saw it. The first time you saw absolute value, you're like, whoa, why is that a V? That's weird. Now it's just like, oh, that's just what it is. Same thing here. Looks kind of weird the first time, but we'll get used to it, and you'll be okay. All right, translations. Usually you guys are all stars at translations. For whatever reason, poke myself on the staple. Our math classes emphasize translations, so we're pretty good at this. So we're probably going to cruise through this. Stop me if we need to explain something, but I think this is going to be familiar. To shift the graph right, you do x minus h. Right, you can almost skip all the words. X minus h pushes it to the right. Pushing it to the left would be x plus h. If you want it to go up, then you put the plus k at the end. If you want it to go down, you put the minus k at the end. If you want to flip it over the x-axis, you put a negative out front. That flips it up and down. I would say it flips it in the y direction. If you want to flip it over the y-axis, meaning if you want to flip it in the x direction, you put a negative in front of the x. Okay, that should be old news. Are we okay with that? You're familiar with that? You've done that 100 times in Algebra 2. Shifting things around, taking those parent functions and moving them up 5 and right 3 and flip them over and stretch them out and all that stuff. What's a little bit harder sometimes is the dilations. These can be more confusing. So here's the graph of x cubed minus 3x. So we're going to do some things to that graph and see what happens. We need to know the difference between, so be careful we get these confused, vertical stretch, vertical compression. So vertical stretch is like you stretch it out. Vertical compression, you squish it down. But we also do a horizontal stretch or horizontal compression. So what would 2 times f of x look like? Well, 2 times, there's our f of x. Multiply everything by 2. And it does probably what you think it would do. It stretches it out 2. A vertical dilation of 2. That would be that one. Let's put this where you can see it. If you put a 1/2 out front, let me back up a second. Anything in with x does something in the x direction, right? So x plus h, x minus h shifts it left and right. A negative in there with x flips it left and right. A multiplier in there with x stretches it left and right. If it's not in there with x, it controls y stuff. So if you put a plus k or minus k at the end, it moves it up or down. If you put a multiplier not on the x but out front, it stretches it or compresses it up and down. So 1/2 is going to squish it. That would be this one. That would be a vertical compression. That we're pretty familiar with. Take the y values and stretch them out or squish them down. Okay, I'm kind of cruising through that. Are we okay with that page? I feel like that's review that you guys are usually pretty good at. Okay, what's a little trickier then is the horizontal stuff. So if you put a 2 in there on x, it's definitely going to affect something in the x direction. And I like to remember it as the x stuff is backwards. So like x plus 3 shifts it to the left 3, right? And x minus 3 shifts it to the right 3. If you multiply the x by 2, it does not stretch it 2, it compresses it by 2. So the x stuff is always backwards. So if we stick a 2x in there, we take our f of x, which was, what was it, x cubed minus 3x. That was our f of x. Pardon my yuckiness there. So if we plug a 2x in there, then it squishes it. So you're multiplying by 2, but because it's in the x, it squishes it down. That would be the horizontal dilation by a factor of 1/2. And if you stick a 1/2 in there, rather than making it smaller like you normally would think a 1/2 would do, the x stuff is backwards. So if you multiply it by 1/2, you actually stretch the graph by 2. So the x stuff is always backwards. This is just the easy way to remember it. It's backwards on the left and right stuff, and it's backwards on the stretch and compress stuff. This next one, this is kind of tricky if we do both a vertical dilation by a factor of 2. So that would mean a 2 out front. A horizontal dilation, a factor of 3. What would the equation look like? Let's see. So vertical by a factor of 2, that would be a 2 out front. Horizontal dilation by a factor of 3. So we want it to grow by a factor of 3. That would be a 1/3 on the inside. Like that. Now, neither one of those is really the answer to this question. 2fx would be the vertical dilation. F of 1/3 x would be the horizontal dilation. So if we wanted to do both, it would be 2 f of 1/3 x. Get my face out of the way there. So the 2 would be the vertical stretch, and the 1/3 would be the horizontal stretch. And then depending on what they wanted, f of x was x cubed minus 3x. So 2 times. Now instead of x cubed, we're going to do 1/3 x cubed minus 3 times 1/3 x. So this isn't wrong, and it kind of depends on what kind of answer they want. That might be okay. But if they want it in terms of x, then we'd have to do all this stuff. So let's see, that'd be x cubed over 27 minus x, and then multiply by 2. 2x cubed over 27 minus 2x would be that picture. Let's look at that picture and see if we can pick out some corresponding points. What time this class ends, so I know whether to speed up or not. There we go, third period, 10:17. Now we're good. We're good. Let's look at some corresponding points and see if this matches what we said was true. So like this point right there that is on the original graph is -1, 2. And I think we can convince ourselves that the corresponding point, like the top of the left hill, if you want to call it that, top of the left hill is -3, 4. So the x value got multiplied by 3, and the y value got multiplied by 2. And that's what we said should happen. Horizontal should be multiplied by 3. -1, 2 turned into -3, 4. Because we multiplied by 3 on the horizontal, and we multiplied by 2 on the vertical. So how to phrase this? If they just give you the picture, then you kind of have to match up corresponding points to figure out what happened. What happened to the x, what happened to the y. And so picking out the corresponding points is the important part. The top of the first hill, the bottom of the second valley, or whatever. And then see what happens to the x's and what happens to the y's. All right, consider the graph below, which is the graph of, so there's our kind of our parent function, well, not parent function, but function we keep working with is this guy, x cubed minus 3x. And the dotted line is g of x. So does that have a horizontal? So I think it's going to have both, but we just need to figure this out. Oh wait, let me read this. Horizontal or vertical shift. Read the word carefully here. Does it shift left or right? Why do you say no? I agree with you, but how do you know? Good. The origin is kind of the key point there. That didn't go anywhere. 0, 0 stays 0, 0. Almost said the origin didn't move, but that's kind of a weird way. The origin never moves. The key origin of the graph didn't go anywhere, so there is no shift either way. Is there a dilation, horizontal or vertical, or both? Okay, both. I like that. I like both. Which one do you want to handle first? Horizontal. Okay. So let's pick out like the key point here. Maybe top of the hill, top of the hill. Negative 1, 2 goes to negative 3, 1. So what's the horizontal dilation? Okay, so let's be careful. I'm going to say it's stretched by 3, which means it's f of 1/3 x. Stretched by 3, which means it's f of 1/3 x. How about the vertical? Compressed by 1/2. So what does that mean in terms of equation? 1/2 f of x. So write an equation. So now I need to like incorporate both of those. So I need the 1/2 out front for the vertical stuff, but I need the 1/3 on the inside for the horizontal stretch. And we want to put it in terms of x, so 1/2. F of x is up here. We're going to fit everything on the page at once here. So 1/3 x cubed minus 3 times 1/3 x. And we could just leave it like that. No need to multiply all that out. Try another one. Same starting graph, x cubed minus 3x. Any shift? Go a little faster on this one. Any shift on this one? Any shift? Not stretched, but shift. No shift. Again, your 0, 0 stays 0, 0. That's kind of the... Okay, how about a dilation? Yes to both. Okay, you guys wanted to do horizontal first, so the left and right stuff. So again, pick out a key point, or a corresponding point. I don't know, you want to do the one on the left or the one... I guess we've been doing the one on the left. Let's stay there. So the original is at negative 1, 2. And the new one is at negative 1/2, 6. So horizontal, we dilated by 1/2. You could say compressed by 1/2. That's fine, but Yeah, that's fine. Dilate by a half, which means f of 2x. And that x is backwards thing. Vertical is always easier, I think. Stretch by 3, so that'd be 3f of x. And putting them together means the 3 is out front and the 2 is inside. The out front makes it vertical, the inside makes it horizontal. So we stretched it by 3 and compressed it by, you could say compressed by 2. I would know what you mean. You're dilating it by a half. So 3 times 2x cubed minus 3 times 2x. That would accomplish the vertical stretch and the horizontal squish. Very technical language. Stretch and squish. 8 minutes left to do the last page. I think we'll be okay. Write an equation of the square root parent function. This is my favorite mistake on this part of the thing is to get all the reflections and translations and everything right, but do squared or absolute value instead of square root. It's like, get the easy part right. Square root reflected across the x-axis. So I know I've got a square root. What is reflected across the x-axis? How do I accomplish that? Negative within, yes. Negative, wait, across the x-axis, that's an up and down, so that's going to be an outside negative. So we can piece this together here. Shifted right 4. So how do I do that? X minus 4. Down 3. Running out of colors. So how do I accomplish down 3? Minus 3 at the end. With a vertical dilation by a factor of 6. Vertical is this way. That's a y thing, so it needs to be outside. So I need a 6 out front. Kind of piece it all together and have a colorful function at that. Why don't you try number 2? And we'll compare.